All right, we are live and ready to continue learning about gradient descent. And as per usual, let me remind you where we kind of got to and left off. And then we'll learn the new stuff today. And today we'll still be working on gradient descent for the whole class. And next class, we'll finish up somewhere in the middle. Okay. And so what is the whole story? Why are we doing gradient descent? Where is it useful for? Well, it's the optimization part of this whole empirical risk minimization algorithm. And really the thing we want to optimize, right, well, minimize in particular, is the empirical risk. And we saw that we could solve for like a closed form solution, which was kind of just an equation that gave us that solution in the previous lectures on optimization. But we saw that, like, can we always do that? And the answer in this gradient descent lecture, at least by this motivating example, is that it turns out that some functions can be convex, such as like this guy, it looks like a bowl. But there really is no closed form solution for W star, the minimizer. However, we'd think that there would still be some nice, like, kind of efficient way to find this. And so for this linear regression setting where we had a linear function class and the squared loss, we do indeed have a closed form solution. So it's not that, exciting for that setting. But we'll see later on for classification that we will indeed pick a loss function that is no longer going to have a closed form solution, and we'll really need to make use of gradient descent. And in general, when the function classes do become more complex, as they do in like practical applications, people will use neural networks. And there, they really are just optimizing them using gradient descent. And the actual functions themselves don't have like closed form solutions. Things also there are usually not convex. And that's more for another course. But the point is that gradient descent is really the approach that people are going to be using for optimizing almost any function. And the other reason for this is also that if you remember in the closed form solution stuff, usually there's going to be a matrix inverse. And calculating an inverse is expensive, which we will kind of see and compare a little bit later in today's lecture and see how gradient descent compares in terms of computational cost. Okay. And so the way we approach this is before directly trying to optimize the empirical risk for our machine learning problem, we had a bit of like a gradient descent and kind of like background without anything to do with machine learning. And that's where we finished last class, and today we're going to get right into the machine learning part. So the thing you really have to keep in mind is there was like the second order gradient descent stuff. I'm just going to jump straight into the first order gradient descent, which is just what people will call regular gradient descent. And I'll just really briefly remind you of this intuition of why it's called gradient descent. And we'll do this through the kind of this picture of optimizing the following function. So let's remind ourselves of what all these lines and things were going on here. So we had this black function. And it's convex. And so it has just one minimum. It has one, the local minimum is the global minimum. And we made some observations, which is, at least in 1D, the derivative is equal to the gradient. And in general, this holds for the gradient, which is if you take the gradient at some point, it tells you, based on its sign, in particular its sign, in what direction you should go to kind of, what will be called is like to take the steepest ascent to increase the function. And since we want to minimize, we're going to want to be descending. So we're going to want to go in the opposite direction of the gradient, because that will give us like the steepest decrease to the function. And the way you do this is you take the gradient and you look at each one of its dimensions, and the sign will tell you in which direction you should go. And then an example of this is like you look at this function here at this point, W not equal to 1. You evaluate its gradient, and here it'll just be the derivative, and you'll find that it's the following like kind of orange line, which is positive. We're going to want to go in the negative direction clearly. And so we take its negative, so that's the descent part. We're descending in the direction of the gradient, or the opposite direction of the gradient. And the question is, how much do you descend? And that is determined by what is called the step size. And that was this like eta term that multiplies your gradient. And we're going to talk about various choices, but roughly speaking, the bigger the step size, the more of a jump you're going to make to your next point. And the smaller the step size, the smaller that jump will be, something like this. And there's kind of like a good way to set this step size, which is by making kind of like 1 over the second derivative. But we said that doing this is usually very computationally kind of expensive to do this calculation, especially in high dimensions. And so we just kind of settle for an approximation, which will just be some number. And it's just going to be a number called the step size. And we kind of want to approximate this sort of correct way of jumping to this minimum. And so in the picture, what happened is we started at W0, we jumped to W1, then we calculated the gradient here, and then we took another step here. And we can keep repeating this process, and the point is you keep getting closer and closer to the minimum of the function. I just remembered there's one thing I just wanted to correct from last lecture in terms of notation, is when we started with these second order gradient descent stuff, you might remember there was like this second order quadratic approximation we had of the function. We talked about finding its minimum and so on. And then we had to rearrange and solve for when this quadratic function's derivative was equal to 0. We had this equation, I rearranged and I wrote the following. And here there was a mistake in the sense that I wrote W star is equal to this. Well, of course, what I meant was the point here, this point, the minimizer of the quadratic function is equal to that. And that is not W star, that is the minimizer of this. And I'll just, for now, write that as W, right? That was just rearranging, solving for W here. And then from now on, we call that W W1 because it was based on W0. And then you keep iterating. So everything else was right. Just note that if you solve this approximate function's minimum, you're not going to get W star. Okay, so that was just to be fixed. So now let's get back to where we were, which was, there was this whole idea of gradient descent, descending in the direction of the negative gradient to get to the minimum. And we left off with just generalizing this to the multidimensional setting. Because obviously in our case, we're going to have features that are multidimensional. We're going to need to optimize over the parameter that's also d+1 dimensional. So this is how this is going to relate. So in this multivariate setting, you just have a variable that's multidimensional. Like in our case, it's always going to be RD or RD+1, as we'll see soon. And the story is, right, we want to find the minimizer of a function, right? This is the value of its input that gives the minimum value. And the gradient descent update rule extends very naturally in the exact way that you would expect to this multivariate case. And that is your next kind of point or your estimate of the minimum is going to be your previous kind of estimate, which is W at time step t, minus some step in the negative gradient, right? So this is the negative gradient. And then it's governed by some step size multiplied by it. And of course, this thing is a vector, right? I can write that. So this guy here is an element of RD. And this will, for the purpose of our class, always be a constant that just multiplies the vector in each component. And in general, this can be some matrix. And we kind of roughly talked about like the optimal matrix is this Hessian, which I learned how to spell last class. And then there's things that people do in between, which is like they pick diagonal matrices, which you can think of as just having a different step size that multiplies each index of this vector, and so on. And there's all sorts of sophisticated methods to kind of, with the least computational cost, kind of get the best approximation to your step sizes. And there's a whole line of research about that. And maybe the other thing to mention is you might be wondering also, like, what is going on with this initial guess? Like, how did we decide W0 should be here and not over here or not over here and so on? And that was completely arbitrary. For the purposes of this class, we're just going to quite literally randomly initialize our initial guess to be, I don't know, we're just going to randomly initialize, literally call like a random number generator and initialize D vectors. However, I do want to mention, similar to step size stuff, there's a whole line of research where people come up with good initialization strategies to initialize, and they're all kind of based on what the problem you might be solving are, what kind of function class you're using, like what kind of neural networks, what kind of loss you're using, and there's all sorts of stories of how to do that. But you can imagine, you know, you have a particular problem, you do some research, you're like, oh, this initialization seems to work for these reasons and others. And yeah, but it's good to know that, you know, this is a serious line of research that lots and lots of work is put into, because it makes a very big difference, as you can see, where you start. If you somehow had some prior knowledge of the type of function class you're working with, if you jump and start like somewhere around the minimum, you're going to get there a lot faster than if you end up picking some really terrible starting point. So that saves you a lot of time in optimization too. Okay, that's kind of a lot of the high level stuff out of the way, and now we can jump into how do we actually do this for the empirical risk, which is what we're trying to minimize. And to do that, before we do that, I forgot that I had some pictures and examples that we can just work through to kind of get more intuition maybe of how it looks like in the multivariate case. So let's do that. So here's a function, multivariate function, over 2 dimensions, or 2 variables. And first, we're going to visualize what this function looks like. It looks like this contour, or whatever you call this thing. And it has a minimum, which I guess I didn't draw, but let's say that minimum is it's somewhere here. I guess I put an X for it. And we're going to work this out very briefly, but the starting point is W0. It's this point here. And after taking one step using some constant step size, which I will tell you what it is in a moment, you get to here, which is closer, you can see, to the minimum. Then you take another step, which is here, and so on. And probably this guy should actually be a lot closer there somewhere. Okay, and the story is if you kept iterating, you would get to that minimum. And there's all sorts of various ways people try to draw this. You can draw like a kind of, I guess these are the level sets, or people call them, I don't know what they call them, but you can draw the values of the function at different levels and draw like a circle. So in this part, the darkest blue would be like this region, and this is all the points where the function is like 1.5, which would be kind of like around here. And then as you get around higher, you're going to get a higher value of the function. So that's something like these sets here, which might be like the value 9, and so on. And so you can visualize that these points are going from points where the function is a larger number to a region where it's smaller and smaller, and eventually approaching this minimum. You can also kind of draw this plot on the right here, where you actually at each point draw what the gradient looks like the direction, and then draw an arrow. Like the longer the arrow means the bigger the gradient is, kind of the steeper it is. And so you can see like outside here, the function is very steep. And you can visually see that, like it is quite steep out here. And as you get closer and closer, the gradients become smaller and smaller, but you can see they're still pointing in the directions you want to be going, which is somewhere around here, which is the minimum. Okay. And so these visualizations are usually done in 2 dimensions, because you can actually easily plot things and get a feel for what it looks like that's more than 1 dimension. But as we get into higher dimensions, you can't plot things, but you're going to have to believe that the same story kind of holds, and usually probably just map that back to your 2-dimensional intuition whenever you kind of get stuck on things. Okay, so let's work through this once for this example, and see what points we get, and see that it is indeed kind of like what is on the plot. Okay, so we have an example. This is our function, and we want to do gradient descent, which really means we're going to make an initial guess of some point, and then we're going to take these gradient steps. So let's calculate the gradients. I'll tell you what our initial guess is. I'll tell you what the step size is in that picture. We'll really quickly calculate some things and see that it checks out. Okay, so remember the gradient, you need to take the partial derivatives of this function. So let's take the partial derivative of g with respect to w1. Well, that is quite easy. That is 2 times w1. Wow, this 2 looks very close to the partial derivative symbol. That's 2. w1 plus e to the w1, and then the other stuff's constant. And then the other partial derivative is the same kind of idea, but for w2. So it's 2 times w2 plus e to the w2. Okay. And so now the question is, what does the gradient kind of like update rule look like? And in particular, that's this thing here. So like the w parameter at step t plus 1 will look like the w parameter at step t. I'm literally just copying and pasting what I told you above, minus some step size at time step t. And then it's times this gradient, right? And so the gradient is going to look like these two partial derivatives plugged in. So this and this. So at the top, it's 2w1 plus e w1 2w2. And maybe to make this more clear, like this thing's a vector. So let's just write it out in like visually vector form. So it has a first index and a second index. Oh, and this is at time step t, of course. And then you end up updating the whole vector at time step t plus 1. So hopefully writing things like this makes it a little more clear. And notice this is all really done component-wise. So this first index gets updated as its previous guess or value times a number multiplied by the gradient. And then you do the same thing for all the others. And you can see that, you know, if you want to be a little more clever, you could pick this thing to be a vector as well, so that you have a different step size in each dimension. All right, so then what did I actually use for the plot below? Well, it turns out that W0 was chosen to be the vector 1, 1. Visually, that should make some sense. 1, 1 is over here. And that's just like the vertical there. And the step size that was used, okay, so W0, that's not where the 0 goes, W0, equals 1, 1. And the step size I used for all time steps, so I'm just going to put for all t, was equal to 1 over 2 plus e. That's just a number. It's a constant number that I used for all values of t. I didn't even change it with time. Okay, and yeah, so then we can do the calculations. So then there's W1. That's what is the value of what is the value of our W, the minimum that we're trying to estimate after one step. And that would just equal to the original value at W0, which is 1, 1, minus the step size, so 1 over 2 plus e. And then you plug in W1 equal to 1 here, and W2, just to be this is, of course, W1 at time step t, W1 at time step t, and W2 at time step t. So for W0, these were 1, this is 1, this is 1. You plug those in, you get this vector. And if you do this calculation, you will see that this is the 0 vector. And if we go down to the plot, you will see that indeed, that is exactly where this green X is. It is at 0, 0. So you move to 0, 0. And you can repeat this and get the purple X, and I'm not going to do that, but that's the story. Okay, and then finally, I just wanted to show a picture of a slightly more complicated looking function in 2 dimensions, which is the following. I don't know, it's some equation. It looks like this, and the minimum is somewhere over here, turns out. And you can, the same story holds. So you'll start at W0 over here. I don't remember what this value was, but it was something. And then you apply gradient descent with a step size of 1 over 6, which I chose because if you made it a lot bigger than that, then what you found is you actually overshot the minimum and things diverged. And if you made it a lot smaller, then the steps looked tiny and you barely made it to the minimum after a few steps. So yeah, this was, I literally just tweaked this a couple of times just to see where it's going. And you'll see that this is really how the step sizes are kind of done and chosen in practice. You kind of try and couple and then see which ones approach the minimum the fastest. Okay. And we can once again look at the plots in these different ways. So this is what I think is called the contour plot. And you can see that here the value of the function, the red region, was really high, and then you keep going down until you approach the kind of the minimal point where it was 0, which is somewhere around here, it turns out. And the same story goes for this process here, where you can see it's following the direction of the gradients. Okay. That's the extent of the visual intuitions. And actually, before we even get to the machine learning thing, I just wanted to mention one more kind of topic, which is selecting these step sizes. And I give you some like very kind of basic ideas that are sometimes used. And just to give you a feel of like what you might want to try to do with just a single constant. Okay, so these are some simple choices. So the first one we've already seen, and that is what is called like the constant step size. And that is where you set your step size eta of t equal to some constant number we'll call eta. That's an element of something greater than 0 and less than infinity. So in this interval. And you just use the same number. And that's actually quite common in a lot of applications, it turns out. Then you can start to be a little bit more creative, and you can kind of observe the first obvious thing you would want, which is like, as time goes on, you're getting closer and closer to the minimum, ideally. And you don't want to keep, taking big steps if you're closer to the minimum. So you're going to somehow want to decrease your step size with time. And there's various ways to decay it. One is by using an inverse function. So this is called like the inverse decaying step size. And that's where you set eta of t to be equal to some constant eta, but now you divide it by t. This is what you want to divide it by. But then you might want to change the scale of how much you're dividing it, so you multiply by another constant. And then you add 1 so that you don't divide by 0 at time step 0. And yeah, so you should really think of this as just approximately 1 over t, and then there's some constants that are being chosen such that, it's not as fast as 1 over t, or it's faster than 1 over t. And yeah, and these parameters like eta and lambda are both elements of 0 to infinity. And just maybe notational point here, which is, you may have already seen this, I don't know if it was ever explicitly mentioned, but when multiple values like eta and lambda all take values in the same set, it's common to write eta, comma lambda, comma b, comma c, element of, and that means each one of them is an element of this. Instead of writing eta, an element of this, comma lambda, an element of this. Okay, just to be clear. Okay, so this is inverse decaying. Sometimes people like a different rate of decay or a different function for decaying, such as an exponential decay. And so that's like another choice. So instead of inverse, you use the exponential. And the exponential is, as you would expect, it's going to be, you take a constant, that's your kind of initial rate, and then you multiply it by 1 over an exponential, or an exponential to the negative power. So 1 over to the exponential at some rate t, so as t increases, the denominator gets bigger, and as usual, you give it some scale lambda, which tells you how kind of quickly that's happening. And so same thing as above, eta and lambda are between 0 and infinity. And so these are also like the parameters you'd kind of tweak when you're trying to run gradient descent. So you might want to, you don't know what values to use for like eta in this case. In this case, you might not know what to use for eta or lambda. So you might try like, I don't know, 5 different values for each one. And then what people say is you sweep over all these values and then pick the one that kind of does the best. And that's called like these are called hyperparameters, and you sweep over your hyperparameters. That's the terminology that's used. Okay, and yeah, maybe I'll write one more. I'm not going to fully define it, but there's another one sort of used called like you might want to normalize by the gradient. And I guess in the PDF notes, there's a little more discussion on this. But it's the same idea. All these kind of have the idea that as your time goes on, you want to divide by some factor that somehow, like depends on time and does something useful. So here you're going to use eta over, I put epsilon, which is just some number so you don't divide by 0, plus what is called the norm of the gradient. And this just measures the size of your gradient. And so, yeah, I'm not going to define this norm thing. It's in the notes. But the point of the story is this, like, this, okay, and it's the 2 norm. But basically, it just measures how long is your vector, which you've seen before. It's quite literally, you take like each component squared and you square root it. So this is like, roughly speaking, the size of your vector, which is your gradient. And so the idea is something like, well, at the beginning, if things are really steep, then you have a giant gradient. And so you might not want to take steps in the negative direction of that giant number, so you kind of normalize by the scale of that gradient. Okay. And so there's all these various things, and quite literally, it's like kind of all heuristics or kind of like problem dependent, which one kind of works, and yeah, and so you play around with these things. But often the best way to start is just pick a constant step size and see if that works. If that's really not working great, then you move on to more sophisticated things. Okay, and then there's other ones called like atom and momentum and things like this that you can use, which we won't talk about in this class. But hopefully you get a sense of like where there's more depth into the topics of machine learning. And that's what other courses kind of dive a little more detail into as well. Okay, so we're finally ready to jump into how this works with our empirical risk and for our machine learning settings. So we finally move on to doing gradient descent. With the empirical risk or estimate of the expected loss. All right, so let's see how this works. So it's been like at least a lecture now since we've talked anything about data sets and predictors and learning and stuff. So let me remind you the setting. And here we don't need anything to do with random data sets, distributions, or anything. We're just, that's for later. So let me just remind you the context again. So we'll have some like fixed data set D. And that'll look like some x1, y1, up to xn, yn, your n data point data set. And we said in last lecture that because we're going to want to use we're going to want to have a bias term in our parameters, at least in this linear function setting. And we'll see that this is going to extend to no matter what functions you use, because you're always going to want to be able to shift your function up or down. So we're going to want this bias term. So to make the math and everything a lot nicer, we add an extra dimension to the input and always say that the 0th index is equal to 1. And so x is going to be our d plus 1, which is where our x's all come from, right? And we're working with regression still, and that's where our labels are going to be real numbers. Okay, so we're in this regression setting. And let me remind you what our function class was. So our function class was all linear functions, which looked like this. It was all functions such that these functions mapped from R, d plus 1. So, you know, vectors, these are your features. There's d features, you add the 1 for the first or the 0th index to R, which is the labels. And it was such that, sometimes I'll write it like this, there's, yeah, such that this f function, when taking some input x, which is some feature, has the form x transpose w, which is that it is the dot product with some parameter vector w, and w is, of course, an element of our d, plus 1. And so this plus 1, once again, is for that bias term, the w naught. Let me just remind you, this guy will look like a w naught, which is a bias term, and then w1 up to wd. That's what that guy looks like. And once again, this allows you to shift your functions up and down. Okay, we used the square loss. So that meant that if you take some y hat as input, which is your prediction, and y as your correct kind of label, the loss is y hat minus y squared. Okay. And now we're finally getting to our objective, which is what we're trying to minimize, and we're going to apply gradient descent to, which is we want to calculate w hat, which is a vector, which is going to be equal to the W that minimizes the following function. So the W vector element of RD plus 1 that minimizes the following function, right? That was L hat of W. And we said that this L hat of W is defined as the empirical risk with a linear predictor. So that was the following. You take the sample mean from your data set of the loss function of your predictor. Your predictor is a linear predictor, right? Let's go up here. It's going to be a predictor coming from this set, right? They always look like this. So I plug in one of those. That's going to look at data point xi. Take the dot product with that. That's your predictor. And you want to compare it to the label yi. And that was the squared loss. So we just have this difference squared. Okay. So now we have set ourselves up to apply gradient descent, and you will see that it is extremely straightforward. So let's remind ourselves, how does this work? What have we been, like everything above, we've had a problem which was something like, I want to minimize some function over some vector W. Well, the only thing that's changed is we've given, so let's go up here. Like we had a picture of a function, right? This was a vector valued function. I could write this as g of W vector, where the W vector has two indices, two parameters, W1, W2. In our case now we have d plus 1 dimensions. And here's a specific function. And for our case, for machine learning, we have a different function. It looks like this. It's just a sum of a bunch of things. So you should think of this guy here as the g of W function that we are minimizing from everything we've seen above. And it is exactly the same setup, right, as we've seen for the closed form solution. And so now let's apply gradient descent to this and see what the update rule will look like. And so now we apply gradient descent. And I will add a little thing in brackets here, because the version of this gradient descent we're about to see is what is often referred to as batch gradient descent. And we'll see why we call this batch, and then we're going to have other versions of it called mini batch gradient descent a little bit later. So we look at batch gradient descent, but you should really, right now, this is just the gradient descent we've always seen. And oh, we'll give this the name BGD, so I don't have to keep writing it. And so now, just to make it very clear what's happening, I'm literally going to go back up to here for the multivariate case. And I'm going to take this equation that we've already seen and just directly apply it to our setup. So that's what we want to do. At this point, you might remember the only thing that's left to do is calculate the gradient. And to calculate the gradient, we need to calculate the partial derivatives of this function. And we've already done that for the closed form solution, if you recall. So when we had to calculate this closed form solution, we had to take the derivative, the partial derivative of this function with respect to each index of W, each dimension, exactly what we need now. And there we just set it to 0 and had to solve that system of equations. Here, we don't have to do any of this business. We just directly plug in the partial derivatives and stack it as a giant vector, and we can do our gradient steps. Okay, and I'm not going to, calculate this partial derivative again from scratch. I'm just going to plug it in from the last class, which was 2 classes ago, and you can go back and review if you don't quite remember what it looked like. So in particular, the thing we need to calculate is this, right? And just to make it absolutely clear, this is the gradient. Well, this is the gradient of this function. What does that look like? That looks like the partial derivatives of L hat with respect to each dimension. So with respect to W naught up to, okay, let me just, up to the partial derivative of L hat with respect to WD transpose. And this is an element of our D plus 1. Makes complete sense because this is an element of our D plus 1. This is an element of our D plus 1. So of course, this should have also D plus 1 dimensions, because the way the update works is you take every dimension and element-wise do the updates, right? Okay. Now I just plug in the definitions of these partial derivatives from the previous class. That was, if you remember, 2 over n times the sum from I equal 1 to n of xi transpose w minus yi times xi, and then it was the index with which we're taking the partial derivative of, so that was 0. And hopefully it's almost like, it's very clear to see that this was the partial derivative. You can kind of like visually see it, like the 2 comes out here because you do the chain rule, then you take the derivative of the inside. In the inside, there's this vector, but we're only caring about the particular index, like 0th index, so that only pops out xi of 0, for instance here. Okay. And then it's up to, and everything's the same as here, so let me just make it clear. I'm going to literally copy this and put it here, and the only thing that changes is the index of xi, so that becomes d. All right. And then this can be kind of simplified a little bit by noticing that, as I said, the only thing that depends on the index is this term here. And so this term here is just a constant. You can pull that out. And so we get that this is equal to, so taking that out as a constant. And now I just have a vector of these xi's. And now the observation is, what is this object? Well, it's exactly just our xi data point, our xi feature. It's just a vector. And so that's equal to this. Okay. So we've got an equation for the gradient, which is quite nice and compact and simple. Yeah. Yeah, so that's our equation. And what does that mean? What is, like, we're basically, we're done here. What that means is our algorithm is as follows, right? And I'm going to write out the pseudocode right now, which is you're going to make an initial guess for W0. You're going to pick some step size based on your favorite step size, whatever method. And then you're just going to iterate some amount of times that you pick yourself. The more you iterate, you're probably going to get closer to the minimum, assuming you chose a good step size. And then you eventually stop, and then you just output the W you got to. Well, in particular, you output the predictor that uses this W. So let's write out that pseudocode. And so now this is going to look a lot closer to what if you ever worked with any machine learning algorithms and so on, kind of looks like, where it becomes this iterative algorithm. And we'll talk about this terminology that people like to use, which they say, like, oh, you can see that it's learning, which really just means that at each iteration is getting closer to the minimum. Okay, so this is your algorithm. It's going to be called batch gradient descent. It's going to be a batch gradient descent linear. So I made this very verbose so that we can compare it to other things. Linear regression learner. Okay, so this is what I called it. And this is particularly for the case with, I'm going to do it for a constant step size, but you could replace it with whatever method you want to set the step size. And you can expect that in the assignments or the midterm or so on, you could be asked, oh, like, what would this algorithm look like? Or where would things change in the pseudocode if you change the step size? Or maybe you change the initialization method or something like this. Oh. And that is indeed where a lot of the fiddling around with these algorithms happens in practice. You try a bunch of different step sizes, initialization methods, and you just kind of see what sticks for your problem. Okay, so what happens? So of course, the first thing that our algorithm takes as input is the data set, just like in the closed form linear regression learner. And that's these xi, x1 till y1 up to xn, yn. But unlike in the closed form solution, we now have what are called hyperparameters. And this is like a big thing where, like, Obviously, you don't want any parameters because you just want to like plug in the input, ideally, and get the solution and be done with it. But unfortunately, for these iterative style algorithms, this is not the case. As we saw, you need to pick a step size. You do need to pick the number of iterations you use. And it becomes, as you get more and more sophisticated, you get more and more hyperparameters, and then people want algorithms that they call are parameter free, and it's a whole ordeal. Okay, so then you actually plug in the step size as well as input, which you, as the algorithm designer, pick, and you plug in the number of iterations, t. And the number of iterations, this thing, instead of calling it iterations, people like to call it the number of epochs. So each one of these gradient descent steps is called an epoch. Yeah, that's all I have to say. That's the correct terminology. And so how does this work? Well, you're gonna have a vector, right? You're gonna have this W vector you're iterating. And you're gonna set it initially to some random vector. You could set it to all zeros. You could set it to a random vector. There's all sorts of empirical / theory work talking about which is better for what cases, but for our course, this is good enough. So you pick a random vector in Rd plus 1. And then you just iterate. So you run a for loop for t equal to 1 up to whatever you chose your parameter as the number of epochs to be. And you run that for loop. So what does it look like? It looks like you calculate so you're going to calculate the gradient of the function you're trying to take gradient steps with respect to. So the gradient is going to be set as what we calculated. Okay. And then all that's left is to update your parameter. So that means set your W parameter vector as the previous W. And so now we're doing pseudocode, right? So it's like W is equal to its previous value. We don't add these superscripts and stuff in pseudocode. Minus the step size. And notice here we're using a constant step size. You can imagine how this is going to change if it's not constant. You might have like a function that you're going to need to call, which is your step size function that outputs the correct step size at each time step. You'll actually implement this in your code. Oh yeah, so next assignment is a coding assignment this Friday where you will implement all these things and visualize what this looks like and yeah, play around with all that. Okay, so yeah, you plug in this gradient that you just calculated, and then you just keep iterating, and whenever you're done, this for loop finishes, you then return. And the return is exactly like before. You're going to return a function f hat, right, which is our function from x to rd plus 1 to r, where its definition is for any input x, right, for any x, any possible feature you could get. Its labeling is as follows. It takes the dot product with that x and the corresponding w you just got to in your final iteration. And that is kind of the most vanilla form of what quite a lot of machine, quite literally, like what a lot of the state-of-the-art stuff is like based on, is the following. And the things that change is that, what things change, right, is like your step size setting is more complicated. The initialization is more complicated. Lucky for you, there's libraries that already people have implemented, and all you do is just call the corresponding initialization method. So like people will write research papers. Then there's going to be research papers that are like heavily cited because these things seem to work in practice. Then PyTorch or TensorFlow, whatever these machine learning libraries are like, oh, this is a really good initialization. Let's implement it. And now whenever you, as a person that wants to run any of these, you just call that corresponding initialization, which already you hope is correctly implemented from the research paper and works well. So, but you in this course, you actually kind of implement these things on your own. But when you actually use it in practice, you just call these libraries, and everything under the hood should be handled correctly. Other things that change is, we're going to see this too, is if your function class gets more complicated. So we move from, let's say, linear functions to polynomials or neural networks or so on. then this gradient calculation here becomes more complicated. It's still the following. It's still all these partial derivatives, but it becomes much more complicated than this. And guess what? In this course, you actually don't have to really do it. In other courses, I think in like the 467 course, you actually do all the calculations for like the gradient for neural networks, and it's kind of annoying. But then when you actually use these things in practice, there's a library that just auto-differentiates this for you. So you just give it a function that, as long as it has derivatives, it can just automatically calculate the derivatives for you, and you never have to do this calculation. So you just call some like auto-differentiation library. And so this is quite literally the structure of your thing. And yeah, so this is an important step, or an important part, I guess, to get to. And there is a question online asking why not t times, this is a long time ago. I think it was for the step size stuff. So let's just have a little glance over here. And it was like, why not t times 1 plus lambda? And I guess, like roughly speaking, it was something like, okay, let me write it. So why not set your step size, I suppose, to something like approximately t, maybe multiply it by lambda, let's say. And the idea is, well, you probably don't want your step size to increase with time, because with time, you're hoping you're getting closer to your minimum. Visually, like, look at this. You're hoping you're getting closer to your minimum. So the last thing you want is to make gigantic jumps as you get further down in time. So usually the idea is that you want the step size to decrease with time. And if you look at the machine learning theory world, people like to precisely classify what exactly is the requirements on the step size decrease rate such that you always guarantee convergence. And then as with like most theory stuff, it's very extreme. So they say like you must decay at least a 1 over t squared rate, t squared. And that becomes like way too fast in practice. But like, why do you do this in theory? Well, because it holds in the worst case. So like, no matter what your data set and what problem you're facing, this will ensure you get there safely. But it's usually very, very conservative. So in practice, like, you really do just try a bunch of random values that you sweep over. Okay. And I guess I'll put an answer. Because it increases with time. Which you do not want. Okay. Cool. Yeah, that's our algorithm. So, what to do next? Well, there's multiple things to kind of. Oh, actually, before even talking about that, let's just get a visual representation of what this is going to look like. Okay, so you got your plot of predicting house prices, as we seem to really like to do in this course. Here you've got, I don't know, let's say, number of rooms. And you got the price up here. And you apply your data that you've gathered, your n data points, and maybe it looks something like this. And okay, maybe you plotted it first, maybe, and you're like, oh, maybe I should just use linear functions. That was maybe your first thing to do, and which we've been doing, so we're in luck, because that's the only thing we know how to do so far. And I will get back to the question a little bit later. And then the question was like, how do we pick the predictor? And in the closed form solution case, our predictor was something along the lines of, well, you take the data, right, in the closed form solution case. There was no parameters or anything. You do some calculations, and you immediately output the thing, and there's no looping, there's no iterating or anything. And that looked like you just output a function directly, which was kind of the one that minimized this empirical risk, and it would look something like this. It has the smallest squared distance between all of these points here. Now, what we can do in this case is, of course, okay, I can still just output, I can give you the picture of what it outputs. But what people like to do in practice, actually, is output the intermediate W's, so like the intermediate functions you get throughout, and see what is like, are you getting closer to minimizing this empirical risk, which should intuitively tell you you're getting better at fitting the data. And so people will say this kind of iterative process is my algorithm is learning, you know, or my I don't know, some learning is going on because you started from some garbage and then you're getting to something better. And what that plot will look like is you can start off and people will like be like, okay, let's plot the first line, the initial guess. And maybe your first plot is like, okay, maybe let's do this so it doesn't split the page weird. Maybe your first guess is this. And you're like, oh dear, that's very not good. So let me just label this guy too. So this would have been like, this green guy would have been like X transpose W, and then we called this the hat, which is like the true minimizer of the empirical risk. And that's what the closed form solution gives us. It really gives us the true minimizer. The purple thing here would be something like X transpose W, our initial guess, which you can see is not looking too good. Then you maybe do like 5 iterations, and you might end up with a line that looks like this. And in the coding assignment, you'll actually have like a slider that you can see what the line kind of changes over time. And it'll look like this, and you can see like, oh, that's getting better. And what's happening under the hood, right? It's minimizing the square distance of these points. They're trying to make that smaller. And visually what you're seeing is that is implying what we wanted, which is that that number, the empirical risk, is somehow telling us that it's fitting the data better. Okay, and so this would be something like X transpose W, maybe 5. And you can do this a lot more, and maybe you do like 100 iterations, and you might end up with a line like this. Let's say. And that's 100. Okay, and actually, hopefully this plot shows a lot, which is if you chose a good step size, this is what you will be seeing. You'll see in the assignments as well, if you choose a bad step size, you're just not going to get any progress. You could even have started with a good guess, and then you might even diverge and start getting worse guesses if you chose a bad step size. But if you chose a good one, you'll see this process, and as the number of iterations, the number of epochs increases, you will approach the closed form solution eventually. And yeah, and so you kind of want this as large as possible. And that's yeah, and that's what people like to call learning. And people also plot like learning curves. And so the learning curve will be like this. You plot your empirical, you plot the empirical risk of the W you've output. And maybe I should put W at time step T. And on the x-axis, you use your time step T, the iteration or the epoch. And what you should see is that at the beginning, you have a terribly high empirical risk. It goes down, and then it just keeps on going down and approaching 0. And eventually, it should get to 0. And yeah, and you can like there's lots of like tools and stuff to plot this live for when you have much bigger. So this like initialization, right? It gives us a line, which we would call the model in machine learning. This is like our model. And of course, there's not that many parameters. I mean, if you make D really, really big, like 10 million or something, or billions, your number of parameters will be very large, and you have a model with that many parameters. And then what you will say is that my model is getting better. My model is learning over time. And what you would see here is like, oh, I have a really bad model at the beginning, bad line. And with time, my model keeps getting better. And these are called like the learning curves. And people will track this for bigger models because this will be running for literally days. So this time could be like one epoch could take like 2-3 hours. And so you'll literally look at this and like you'll come in, you'll run this, you go to bed, come in the next day, and you're like, oh, I've made it here. It's looking good because maybe in like a week or so I can be here and maybe I'll stop. Yeah. Say that again, sorry. Yeah. No, so this is the actual loss, right? So what you're plotting is this guy here. You're plotting this, and gradient descent should be minimizing this function, right? So like if we think of this as the G of W thing, visually, that should be, I mean, it should be the same story as this, which is like, you're plotting the value of the function, and you keep going and decreasing, and eventually the claim is that you should be able, if it's, okay, you should be able to approach something close to 0, and it probably won't get quite to 0, because you can see in this example here that clearly it's like even the perfect line will have some error, right? And so that is a very good point. So unless you can perfectly fit the data with the model you chose, this will approach some like best possible fit with a line. Yeah, that's a good point. But yeah, okay, that's a great point. So this is kind of, and this is exactly the value of L hat of the closed form solution, because this is the minimizer. Okay, so that's what you're approaching. And okay, so that's the story. Yeah, and anyways, the question online, I agree, it is a trivial difference where the thing that they proposed is it's just a different way to scale by some numbers and so on for the step size stuff. Okay, so this is what you should really keep in mind. And we talked about these different things that you can change and so on. And there's another thing you can actually change, which we're going to get into in a slight second. But it's going to be all about computation now, kind of, which is, yeah, like why, first of all, if you can get a closed form solution for like this linear regression case, is there even any value in doing this gradient stuff? So we're going to talk about how much like computation this takes and if it's more efficient and so on. Like we're going to talk about that. And we're going to see another thing, which is like, imagine you had a gigantic data set. Like, let's say, imagine like you had like 10 trillion data points, right? And let's say like the bigger the data set, right, the better your estimate is going to be of L hat. And so therefore the gradient is also going to be like kind of in the right direction, or it's going to be a good estimate of the true gradient of the actual L, so not L hat. And so the story is going to be like, if you have so much data, do you really need to do this calculation for all your data? Like, is this really necessary? Or can you do it for like a subset of your data? Because at the end of the day, this is going to be extremely expensive. You're going to have to iterate over every single data point and do this calculation. And then after all that iteration, like of 10 trillion data points, what happens? You take one gradient step. That's not maybe that exciting because we saw you're going to need to take a lot of them. So you can save a lot on this, it turns out. If you have big data sets, turns out it's not even like that big. You can batch it up into smaller calculations of this estimate, of this empirical risk, and do smaller steps. So they'll be like kind of less precise. However, you can do them much more efficiently, and it turns out to usually be a good idea. So these are going to be the two things we try to introduce now, which is the computational costs, and then improving it as well by, instead of using batch gradient descent, batch meaning you use the whole batch of data, into using mini batch gradient descent, which is you batch things up into mini batches. And that's going to be another hyperparameter that people choose between, which is the size of these batches. Okay, so that's the overview. And now let's do this. So the first thing we want to do is compare the computation of the closed form solution versus batch gradient descent. Okay. And we're going to do this with defining as minimal computational complexity notation as possible, but hopefully still giving you the right, the correct vibes of what's going on here. But just like a rough, like how many people have taken like an algorithms course before where you talked about like the runtime of sorting a list? Okay, we got, I think, at least half the class, but that's going to be roughly the idea, right? We have an algorithm here. We're not sorting a list. We're trying to find the minimizer over some data set thing. And we're going to ask, what is the runtime of our algorithm? And you might remember the way we talk about this at like a high level is that you just look at the number of elementary operations that our algorithm does, which is like the number of addition, multiplication, kind of division steps. And then if you have a for loop, you know, that does that many times, and you're just going to sum that all up. And we're going to see what that function looks like, the number of operations as something scales, right? And that's something that we're going to talk about scaling is going to be like the number of data points. So how does the number of data points affect the number of computation we do? How does the size of the features affect that? And this should be mapped to kind of like, if you have a list that you need to sort, you might talk about how much computation do I need to do as the size of the list grows, then how does, yeah, okay. And this is a whole other area of kind of machine learning. Like all this stuff is important, but people kind of like to sometimes study this individually, which is they first ask like, you know, forgetting about the runtime of my algorithm, like how efficient is it in terms of data? Like how much data do I kind of need to get to this solution? That's one thing they ask. Another thing, which we're looking at kind of now, is like how long does my algorithm take to actually run? And there's various trade-offs in these. Okay, so let's learn about this. So the idea of this is we're going to talk about like the number of computational steps. We're going to want to count the number of computational steps, which roughly speaking is going to be the number of elementary operations. So these are at a high level things like how many times have you added, subtracted, multiplied, etc. And these are what we will call like run in constant time. Okay. And that's because on a computer, this can be implemented in what is roughly some constant amount of manipulations of, what are they called? Somehow I forgot what the whole, what are the little switches called again? On like on a chip. Does anyone remember? It's not a transformer. What is it called? A transistor. Great. Thank you. You'd think I should know the name of that, but now we know. Okay. So yeah, so it's like there's a kind of a constant number of these transistor operations that happen. Okay, cool. So, and the way we talk about this is using what is big O notation. Okay, and you should think about this as follows, right? Because we're going to talk about how does like the number of operations scale with different variables. And so here I just jump into just some kind of mathematical notation of what this big O notation means. Roughly speaking, you just want to try to eliminate any like what are called slower growing functions and constant terms that multiply these functions, because you don't want to care about it. So you're going to say something like a function is equal to big O of some other function g of n. And this is probably going to look very abstract, if the following kind of thing holds. And I'll draw a plot first. So suppose you have like some function. And we're going to pick our favorite kind of function, which is the squared function. And maybe it looks like this. That was interesting. Okay, didn't like that. Okay, so pick some squared function. Let's say this function here is f of n, and it's equal to 2n squared plus 3. So like this point here is 3. And what we're roughly going to say, so like the example is going to be the following. There's going to be the example of how this works, which is we're going to say that 2n squared plus 3 is, okay, maybe I'll write more formal. So people use this equals to, really I should put, so this is a set of functions, and we're going to say it's an element of this set. If, well, I'm going to write it out in a second, but you would say that this is in big O of n squared. And so the idea is that this function grows at most kind of as fast as n squared. Okay? And the way we're going to frame this like precisely is we're going to say I can find a function n squared that when scaled by a constant, at some point will just always be larger than the other function. Okay? So that means I can find some other function, n squared, that has no constant terms and whatever. It's just going to be a squared function. And I'll scale it by some other constant like 3. So I'll do 3n squared, for instance. Maybe this is 3n squared. That after some point here, it is just always bigger than the other function. Okay? And so this is a way to just like characterize that, you know, all these functions that have different constants here or add other terms that are smaller than n squared are really kind of growing at the same rate as n gets large enough, which is at this like kind of n squared rate, or if it was n cubed, or so on, so on. Okay, so for instance, the way you would do this is, okay, formally, this notation is going to mean, let me just put the formal definition. So it's going to mean that f of n is going to be less than or equal to some constant times the function g of n that we plugged in here for n greater than some n naught. So n naught is going to be the point. This will be n naught here. This is the point after which the function is just always bigger, and some constant that's in a real number. Maybe I'll put positive real number. Okay. And so in this example, we would say the following, which is this is in this thing, because if I set, well, let's look at this thing, right? So, okay, this is n naught. Well, at what n naught is this thing just strictly bigger? You can just like play around with it, or you can rearrange and solve this system of equations. But I'm going to tell you that if you pick n to be equal to, I guess, 2. So if you set n naught equal to 2, well, what is this function? F of n at 2 is equal to 2 times 4 plus 3, that's 11. And the function above here, evaluated at 2, is equal to 3 times 4, which is 12. So that's going to be just strictly larger. So, yeah. And n naught should also be an element of, so I'll write it like this, element of a natural number. So this point would actually be like visually somewhere a little bit to the right. That would be like n naught. Okay, so if n naught equals to 2 and c equals to 3, then 2 squared plus 3 is greater than 3 2 squared, which is, sorry, other way around. 11 is less than or equal to 12. And you can check that for any n greater than 2, this still keeps holding. Okay, anyways, this is going to be the motivation. You're going to, because at the end of the day, we're going to end up with a bunch of functions like this, where it's going to be like some constant. Maybe you do like n up, maybe you look through it, let's like in the list case, if you want to sort a list, maybe you loop through the list once and then you loop through the list a second time. We're just going to say that's basically of the same order of like computation time. Although that is 2 times n, we're just going to say it's in big O of n. So we're just going to keep using this and not count all these constants, and that's how it's usually done for computation. Okay, so now let's study this for the machine learning case. So what were we doing? So in the closed form case solution, what did it look like? In the closed form solution, we had the W hat was equal to A matrix inverse B vector, where the A matrix was equal to the sum I equal 1 to n of xi transpose, which we called an outer product. Or you could think of it's like a matrix multiply, where this is a row vector and this is a column vector and this is a row vector. And then you matrix multiply these two, which is like you take this, multiply through everything, take this, multiply through everything, and you get a matrix returned. That's that guy. And then there's B vector, which is going to be written down here. And this, if you don't remember, this we calculated before. So you probably don't remember this. But if you go back, I assure you, this is something we calculated. But what you need to know is we had some mathematical operation that you had to execute on a computer, and we want to ask how many operations were done. Okay, and the way you do this is you just break it up into all the steps. So here's how the computation looks. So computing, let's see, computing different things. So computing A, right? That's the first thing if you remember our algorithm, it computes A. Well, how many operations does it take? This is going to do a calculation like this. How does that work? I told you, roughly speaking, the visual was you take every element of this, you multiply it by every element in that column, and you're going to need to do that for every single element of this. There's d plus 1 elements here, d plus 1 elements here. You multiply the two, you get d squared plus 2d plus 2. You can already see that that function is very annoying to write out, so d squared plus 2d plus 1 is in big O of d squared. So we're going to make use of that already. So this inner operation is already big O of d squared. There's d squared operations that happen. And then you have a sum. So you do that n times. So just calculating this thing is going to take n, or big O, of n times d squared. And if you wrote out this explicitly, it would actually be n times d squared plus 2d plus 1. So we're saving some ink. Then we move on to calculating the b vector. What is that going to be? That's going to be big O of a vector times a constant. Well, you just take the constant, multiply each index. That's d operations, d plus 1 operations, times n. This is like a for loop, right, on a computer. So that would be n times d plus 1, which is big O of n times d. Then there's a matrix inverse operation. And that, I just tell you, is no more than d cubed. So this is definitely true. Turns out you can do this in no more than d cubed operations. And a unbelievable amount of research goes into trying to see how small can you make this. And I don't remember what the current best is, but I know that actually using machine learning models, this company called Google DeepMind, I'm pretty sure, like a couple years ago came up with a slightly more efficient way of calculating these matrix inverses, which turns out actually, well, you can kind of maybe see that there's a lot of matrix multiply or vector matrix multiply stuff that happens in this loop. And I told you this is what really happens in machine learning. And I told you that this will run for days and days. So you can imagine even like a tiny saving in that exponent is an unbelievable saving in terms of cost and everything. So it's a very lucrative enterprise if you find slight improvements to this. And then we can also talk about, okay, just like I'm just rambling on, but I think it's kind of interesting, is in this computational like complexity world, people talk about what is like, you can actually show that exists no algorithm that can do something more efficiently than something. And like just to give you a kind of like a flavor of this, when you sort a list, you can very easily show that there exists no algorithm that can run in time less than the length of the list. Because roughly speaking, you at least have to check each element of the list once to be able to see what's there. And you can do the same thing for matrix multiplies. And there's like what are called lower bounds, which say what is the minimum time you need to run. And I think that is something of the order like 2 to the power, or sorry, d to the power of 2.2 or something like that. I think this Google ones was like 2 to the 3 point something. And so there is this gap. And it's people are really curious to see how close you can get. So anyways, interesting line of work. But it's very important because these operations happen a lot. Okay. And then the final operation is this guy, which is multiplying these two. And this is just a matrix vector multiply, which is you take this guy, you multiply. If you remember, it was just d dot products. And each dot product takes time d. And so it becomes d squared. Right? Roughly speaking, let me just show you the visual. You have this matrix. You treat it as a bunch of rows. You have this one vector here. You take this vector and you multiply, dot product it with this. Then you dot product it with this. So there's d rows here. And each dot product operation multiplies d numbers, right? It's the sum of each index multiplied. So that's d squared. Okay, so we got this whole thing. And remember the way this worked was we did this in a step-by-step manner. So really it would be, I need to run for this long, then I run for this long, so that would be added. plus this, plus this. And so maybe to make this absolutely explicit, the total compute is big O of nd squared plus nd plus d cubed plus d squared. And this can be simplified because this term dominates this. There's just a constant here. And this term, this term is also dominated by this because the d only has an exponent of 1. And so this becomes nd squared plus d cubed. Okay, so roughly speaking, you're going to do, if n, for instance, if n is less than d, then this will just be d cubed, because then it would be like some number less than d cubed plus d cubed. And if n is larger than d, which actually in like the real world, n is usually smaller than d, just to give you a sense, like n might be in the billions and d might be in the trillions of size. So it's around like this d cubed thing. So you're really not going to want to run matrix inverses, let's say, because that's really the culprit here. Okay, so what is it for batch gradient descent? And I'm seeing that we're running low on time here. So yeah, we can work it out. Okay, so let's just look at the computation. What do we need to compute? So let's look at our algorithm, because it's not just, I guess, one line thing. So you're going to need to do, it's still very simple, right? You need to calculate this, and then you need to calculate this. All right, so what does this look like? Let's just do it in words, and then maybe we'll go into more detail, probably not next class. But let's look at this. First, inside, right? Because we know this is going to be looped n times. So what's happening inside? Inside, I have a dot product. That we said is just a sum, right? It's a sum of d multiplies. Then you take a vector and you subtract another vector. That's going to take d operations as well, because you do it element-wise subtraction. Then you have another, so this is a number. And then you have a number times a vector. Well, that's, once again, just d operations. So you end up with actually 3 times d operations to execute this. That's just big O of d. Then you have a sum over n, so that's n times d. And then you multiply by a constant, which is just constant time. And so this calculation is going to take you n times d time. So computing the gradient is going to be big O of n times d. Then doing the W update, I'll just put that, is also really easy. It's you take a vector, you subtract from it another vector. That takes d time, so that's very small. And then you have to remember that the for loop is going to do this. That's not how you spell. I was trying to talk and write. You got to remember the for loop does this t times, number of epochs times. So this whole thing gets big O of t times n times d. Okay. And so now we compare the two, and I will end on that. Yeah, so we're going to compare. So these are the two things we want to compare. Big O of t and d versus big O of nd squared plus d cubed. Okay. And so you can do various case analysis and stuff, but the kind of the big one we're going to look at is if your number of iterations is less than d, so strictly less than the dimension d, and I told you d can be like in the trillions. So if you're doing like, 10, 20, or 1,000 or 100,000 epochs, it still could be quite small. Well, then big O of t and d is no larger, right? So t and d is going to be no larger than big O of nd squared, because I've just replaced t with a bigger number, d, which is no larger than big O of nd squared plus d cubed. And so, yeah, so roughly speaking, we can see that and there's a strict inequality because this was strict. we can see that the saving is when you have to run less epochs than the number of dimensions of your features or your parameters, then it's going to be more computationally efficient. And yeah. Okay, so that's where I'm going to end. We'll continue next class about talking about this mini batch gradient descent.